给大家的就是9:03，好不好？这是我自己平常就是 meeting 啊，就是如果今天没有办法在9:0，就是01分迟到1分钟之内，就是问号，我就会跟学生讲说，哎，不好意思，我会迟到5分钟，或者迟到3分钟这样。然后大家也会发现，其实 iPad 的字也蛮难写的，对不对？Sorry，可能不行了。好，非常感谢各位，真的是，对，准时是非常非常不容易的事情，太佩服各位了。不得不说，我小时候当大学生的时候，研究生的时候，我也没有这么准时，所以大家都比我当时表现还要好，谢谢大家这些同学。好，那应该就等下不好意思，再做一件事情。哎，我录了没啊？
好像还没。
我还没录吗？Stop，录了。OK，请问线上同学听得到我讲话吗？如果听得到的话，请举个手，嘟嘟嘟嘟嘟这样子。耶，谢谢。好，那我们就开始了。非常感谢各位。好，那我们上周是采取就是我目前任教以来第一次就是停课的时候，就是上传我去年的上课内容。实际上我已经教这门课大概10年左右，所以说上一年度教的东西跟今年会几乎是完全一样的哈。那纯粹就只是现在的头发少一点，然后上一次的头发多一点，就只是这样而已。那不知道大家有没有上线去看？然后我找到的是2000吗？不是讲说2020年的。那后来丽君有补充一个2022年，解析度比较高啦，好，那都可以，好，这两个都可以。那我是以2020年的那个3小时的长度，那就看大家就是 O 不 OK。哦，Sorry，I should speak English. Sorry. It's my very first time to upload my previous video when I have to stop the course, skip the week. Okay, so I hope all of you um, go on the Facebook and to see the uploaded video. And the video version was 2020. Sorry for the low resolution, but Li Jun found another version. She kept the 2022 version, so they have relatively high resolution. So hope you enjoy the courses. And yeah, it starts from the statistic. I mean, PDF 5 to PDF 6 in the middle of the PDF 6. I hope you all read through it, and understand all of them. And I will give a really quick review from now. And the reason why I'm doing this upload things is because a lot of students asking me, especially international student, they want to set the flight ticket right after semester. I understand that because when I study abroad, I really want to go home to see my friends, yes, and parents, yes. So I will try my best to keep the course stopping at before the semester ending. Okay, the end of semester. So yeah, so I will upload twice. Last week and the week that the sport event in our NYCU. Okay, so I hope everyone can learn that by the internet. So I will give a really quick. I shouldn't give this. Oh, it's okay. It's okay. Wait a minute. Sorry. 小抄 Okay. Last week, last week, the week before the last week, I guess I stopped here, right? Because we talk about the limitation, the condition we set, NVU, a fixed NVU, and then we need to obey the particle numbers and the energy U. So we need to list all the possibility to fit the energy and the particles number. Okay, so this is a table. Okay, and then we found that the middle part is the most disordered part, which means that when we have more particles, mostly if we choose, I mean, the system will represent to you in the real world will always in the most disordered region. Okay, they have higher possibility. True possibility is 0.6, right? And then we use ensemble is a concept. It's just a concept. You can imagine that when you are going to measure things precisely, you need to measure long time and average them. So we need if we have multiple identical systems and then measure them once and then average them, it should be really similar to long time average pressure. This is called ensemble. Ensemble is really useful when we are doing simulation nowadays, because simulation typically will simulate particular time step. Okay, so typically it is because sometimes everything has some randomness involved. So if you just simulate once, it's not representative. You should simulate 5, 6, 10 times to average all this, all the results to eliminate the randomness. So this is also the ensemble means. Okay, ensemble average. And we have a type of ensemble: microcanonical, canonical, and grand canonical. The differences of this are the how we define the system: NVU, NVT, and mu VT, something like that. Okay, but it's okay. And also the microcanonical ensemble, we have the assumption that every state has equal possibility, no preference state. And this is a canonical ensemble example, 2 examples. And then you can notice that at different time step, time t and time prime, okay, they have these rectangular, these grids, okay, these grids, they contain different container. You can imagine that different states. Although you think, oh, they will change with the time, but the overall distribution between the time t and time t prime are the same. The distribution are the same, average are the same, but each member of ensemble will not be the same. But it's okay because the randomness involved. But after you do the distribution, you do the average, they will be the same. Okay, so this is the concept of the canonical ensemble means. And also, this is example 2. We have a very large water cooler, and the bottle container contain 10 to 25 molecules, and volume are fixed. And then we're going to see if you are picking one bottle, what is the probability you pick the bottle has the energy EI. Okay, and we just want to see the number of states before we calculate the possibility, right? So we need to find that actually this is a really important concept in this page. We mentioned that in my video, sorry. In my video, I said actually when we compare 2 states, actually the absolute value of the energy are not the key, not the key. Absolute value are not the key. The difference is, okay, because the reference point, 0 point for people, for human, we can set different origin. We can set 0 points, whatever we want. So actually, the difference between the energy states are the most important thing. So that's the reason why we changed the F as the EJ minus EK. Okay, so that's the main things. And then because we changed that things, we found the behavior of the function. So we can find actually they have the similar. I mean, they have the behavior. So we can write down. We can solve that. And after we solve that, okay, the AI equal to C exponential minus beta EI. So that's what we learned in my video, and then we modify to calculate true possibility, and then we do the calculation, and then we found that we just this Q is actually sum over the states, all over the states, or all available quantum states. And then we found that, the partition function is actually the accessible number of energy state. So we named partition function Z or Q, okay? They actually all the sum over states, okay? So it can be put in the divisions button of under the division sign, 在下面了哈，除号的下面。Okay, and after that, we found that the partition function has the behavior that if you have a higher temperature, you will have lower possibility. If you have higher temperature, you will excite the particle to the higher level energy level. Okay, Or if this material you receive in your in front of you, and the material has really great, large energy gap, which means that particle cannot easily jump to the next. So most of the particle will distribute at the lowest level. So that basically let you know the system, particle in system, how easily it jump to the next level. Okay, and it will connect it to the S entropy. Okay, and then the most important part for this page is that the Q and Z are different, but I mean they are the same, but in the symbol they are different. Q is actually from other textbooks, but Z is written down in our textbook. But Q and Z are actually the same. They are describing the same thing. Just become when you summation previously, the Z is actually the level, the energy level, sum through energy level. You see the bottom part here. Okay, and then we can finally connect the thermodynamic probability to entropy by using S equal to K natural log W. Natural log W can be related to the distribution, right? So when we say S equal to K natural log W, which means that we can use W to calculate other material properties used frequently in classical thermodynamics. This is a bridge. This is a bridge shown here. Okay, and then we found that we can find the particle in the box. We want to see how energy level and the movement of the particles. Okay, and then we found that when you see the particle in the box, you need to use quantum mechanics and waves to calculate their energy. Okay, and this is the energy. How you calculate that? Difficult. But it's interesting that the energy epsilon can be calculated by these quantum numbers, right? And then because quantum number is all related to the energy, all related to waveform. Okay, so you can see the first mode and second mode and third mode, and you can see that they actually quantized because you have one mole, first mole, second mole, and third mole. So you can see energy are quantized. And by examining all these, you can list all the possibility, and then you can see, you can write down epsilon 1, epsilon 2, epsilon 3. So maybe you can try that by yourself in your home, okay? At your home, I believe this is useful, okay? And then we found that quantum number are really large number. So which means that the large number means that they are almost continuous when we, see in the macroscopic view. And because they can be treated as almost continuously, we can estimate their degeneracy by calculating the volume. Why volume are connected to the number? Because actually when we calculate volume, it's calculating a cubic. Each cubic is 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. And then when we sum them up, all the 1 unit cubic, to sum them up together, it becomes our volume. So that's the reason why if we set every corner, one cubic with 1 point, and then you calculate volume, which means that you calculate how many points in that region, right? So that's how we calculate, estimate degeneracy by using this mathematical technique. Okay, and then yeah, that's it. And then we just calculate the track practice and example. Good. And then, sorry, this is really quick because I assume that you have done the recording. You watched my recording, right? Okay, and then I also start to talk about classical and quantum statistics, and we want to calculate the Boltzmann statistic. Boltzmann statistic is describing distinguishable, or very important, distinguishable as solid and liquid, and we need to obey, of course, conservation of particles, conservation of energy, and our goal is try to find the occupation number for each energy level when the thermodynamic probability is a maximum. Okay, so which means that we want to find, in other words, we want to find the equilibrium state, because every time you pick up this system, the occupation number has highest possibility for you to pick up. So almost every time you could pick up the same state, similar states. So this is how we want to find the set of occupation number in each energy level. So this is not easy. Let's take a look. So before we go into find the highest possibility occupation number, we need to find the how many possibility. So that's how we get it. Yeah. And then we found that the Boltzmann statistics is that the WB, N1, N2, N. The WB means the statistic of Boltzmann, okay? And N1, N2, of course, N1 is the occupation number for the energy level 1. N2 is particle number for energy level 2. Okay, so for suppose 10, 20, 30, 21, 100, blah, 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 blah. And with that distribution, and if you input those N1, N2 set N1, N2, and you can get the WB value, thermodynamic probability, with that big equation in the red square. Okay, but this is just a formulation. We need to find what kind of the set can make this red box maxima. That's our purpose. Okay, so this is what we are going to do. How can we get the maxima? We are using Lagrange multiplier, and then we talk about Lagrange multiplier is a mathematical skills which can tell us. We just introducing a new function and adding 2 extra terms if you have the constraint. 2 constraints. If you have 2 constraints. The first constraint is that x, and the other is y, and then we just write it down in the end of the new function. Okay, and then we just do the partial differentiation. So each of them will become 0, 0. I mean, if you just do the differentiation, everyone will be 0 because we want to find the maxima, right? So we just do the differentiation equal to 0, and then we can obtain equation n plus 2 equations, and we have unknown n plus 2. So that means that we can determine the formulation for N1, N2, N3, N4, N5, and also alpha and beta. Okay, and then 应该就结束了吧 Okay, so I spent like 20 minutes to summarize what we taught in last week. I hope you can understand that because it was a little bit fast and okay. Wait a minute. 你这边教了吗？这边好像还没教哈。好 ，So let's continue. So our goal is that we're going to differentiate every term, and to make it 0, and we can solve that. Then our goal is that we want to maximize the W. It's a function of N1, N2, N3, Nn, and the W equal to the right hand side. That's that ugly things. Okay, we want to determine that. We want to determine these things to maximize this one. Okay, that's our purpose. Okay. Okay, so let's continue. But you can notice that this pi here is multiple multiplication, times. So this is not easy for us. So what we're going to do is we want to maximize W, but this is really difficult. So why not we change to simplify our problem? We do natural log W. Because the natural log W, if we can plot the natural log X plot, you can see that this is actually 1 to 1. If you have a 1 Y, you have automatically mapping to an X value. So actually you maximize the natural log W, you maximize your original W. Okay, because your X and Y are 1 to 1 mapping. Okay, so we do the natural log. It won't affect what we are going to do. Okay, because natural log W, you maximize natural log W, you naturally maximize the W. Okay, so that's how we try to make it easier. And the constraint will be n sigma nj become m total number. Sigma mj epsilon j summed up together become the internal energy. That's our 2 constraints. Okay, and then we can just write it down. So epsilon j will be a constant. Okay. Then we can write down the new function in just like this, and then we do the differentiation for nj. And then it will look like this. And for if we do the differentiation to alpha and beta, the 2 Lagrange multiplier, you have this one become the constraint 1. This become constraint 2. Okay, so then we will going to solve these equations to get the distribution of N1, N2, and distribution of that. OK， 好，我们终于要接，就是我刚刚花了20分钟的来回顾一下那个。那我们总之就是我们希望要找到一个 N1 一个 set 哦，一个 N1、N2、N3 到底长什么样子，一整个数串这个数串呢会让 W 最大值。那很难了但是至少我们就有一个 Lagrange multiplier 这个东西去帮助我们去计算出来。那当然我们会有一些 constraint， 就是束缚条件，我们一定要满足的。然后呢，接下来这个 W 呢会写成这样，这是一个连乘的符号。连乘对我来讲都是比较难的嘛，对不对哈？所以说我们想要取个 natural log W， 让这个连乘变成连加，那这样不是事情会比较好办吗？那可能会觉得同学会觉得说，我是要最大化这个，不是要最大化 natural log W 其实没有关系，原因是因为 natural log W 的线画成在这里的话，你会发现每一个点 natural log W 的点会跟你的 x 轴是 x 值 input 的值是一样的，你的 natural log W 越大，那它就是越大，对不对哈？所以它们俩是1对1之间的关系，所以你最大化 natural log W 其实你就是最大化 W。OK， 好，那所以这边就让问题变简单了，然后我们就依照前面那一页把 Lagrange multiplier 的新的 function 写出来，然后再对每一个 n1、n2、n3、nn 来做微分，它会写成这样子。然后对 Lagrange multiplier 的第一个 alpha 就微分起来以后，就发现它根本就是 constraint 那个式子嘛，然后 beta 也是它的 constraint 的式子，第二个式子。所以我们接下来可以去解这一大堆，然后去找 N1、N2、N3 它会长什么样子，它会让 W 最大化。Okay, next. So if we can successfully do that, we can find the set of W1, W2, Wn to maximize W. So the Boltzmann distribution is, the natural W is natural log m factorial and blah 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 and blah blah blah. Okay, so we do the this one. We can do the Stirling approximation. Okay, so we can have this one into that one. So no problem. I guess you can understand that. And then we're going to do the differentiation, right? To nj, n1, n2, n3. Okay, so let's do this. And then we notice that where is that? Because it become, this one, n factorial. N factorial is a total number. N is a constant, right? So if you have n constant partial differentiation to nj, it will automatically go to 0 if we do the differentiation. So there's nothing here for the first term because it will gone if you do the differentiation for nj. No matter it's n1, n2, n3, no matter, because this is constant, right? So it gone here, nothing here. So next will be the second part and third part. Okay, that's the reason why we only have that. Should I write down this? You will make it 0. Becomes 0. Okay, so nothing else. And then we are going to do the differentiation, right? But don't forget, we still have the Lagrange multiplier term, alpha nj sigma mi I plus beta alpha nj sigma I mi epsilon I equal to 0. Okay, so this is actually the new function which partial differentiation for ni looks like. Sorry, nj looks like. So there's a really, it looks really terrifying, right? Wow, it's a summation and you're going to do the differentiation for nj. There are many, uncertainty inside, but actually it is simpler than you think, okay, than you thought. You see, nj and mi, when you do the differentiation, only effective term will occur is when I equal to j. You can imagine that this is n1. This is n1. Okay, n1 differentiate n1. affected. Good. But N1 differentiate N2. No, it doesn't actually, it becomes 0, right? N1 and 3 become 0. So only if I equal to j, the term is non-zero. So everything is simpler than you think. So now, if you do the differentiation, only nj and gj will left. Otherwise, they are all 0. So you can see here become natural log gj. Good. And here become natural log nj. Because here this is a multiplier. So I just okay, because you can differentiate the front and then times the back, and you left the front and differentiate the back. Okay, so you can this after you do the differentiation. Yes, only natural log nj and minus nj over nj, because this 1 over nj is differentiation of natural log nj. Okay, and then this one is also right, because nj differentiate nj, of course, this become 1. And here is alpha, and here is beta epsilon j equal to 0. So everything is easy. And then you can have this one, natural log nj over gj equal to alpha 加 beta, plus beta epsilon j. And then you can have this one. And then we can define that this nj over gj is fj is a function of epsilon j, because you see it determined by epsilon j. Right, so Boltzmann distribution function, but we don't know alpha and beta. Okay, so if the n1, n2, n3 satisfy with this ratio equal to this one, it will make the W maximum. Okay, so this is actually the key. Is a key to seek to find the equilibrium state. Okay, the degeneracy and NJ ratio need to be this one, need to be equal to this value. And if we satisfy with this form, the system is equilibrium. It has highest possibility. OK， 好，这一页我觉得有点需要，就是很重要哈，就是我们要做Boltzmann distribution 的话，我们要去找 natural log W 嘛哈，然后这边已经写出来，这没有问题。然后后面这个东西接成 the Stirling approximation 就得到这一个式子。第一项 n x factorial 为什么不在这里呢？因为它的 n factorial 是一个常数，所以你做了微分以后就不见了，所以根本不用管它。然后后面就变成这里啦。那这里的话，后面别忘了还有那个 alpha 跟 beta 的的那个项，我们要对于 nj 做微分。但可能会怕就是怎么 nj 有 sigma 好难微分哦，但实际上不用紧张，因为呢 nj 是 n1 n2 n3 n4， 但里面也有 ni 啊n1 n2 n3 n4， 只有在 n1 跟 n1 的 i 跟 j 是相等的状况下的时候，它的微分才不会等于0，因为如果你是用 n2 去微分 n1， 那根本也是0嘛，因为是 partial differentiation， 所以说只有 i 等于 j 的时候会是 non-zero。好，那时候算一算就发现只剩下这些 term， 好，只剩下这些 term， 然后动作的话就变这样子了。好，那这个东西呢，我们是给我们一个意思，就是说我们刚刚不是要找 n1 n2 n3 的长相吗？那要怎么长？就是要怎么样长相它才会有最大的几率呢？当它的nj 跟它的 gj， 也就是它的那一个 energy level 的 degeneracy 的个数的比值。会等于这个数字的时候，每一阶都要这样子每一阶都去看说我们的阶层的阶数，我们的阶的里面的 particle number 跟 gj 的 ratio 如果等于这个的话，你就是最大值，你就是最稳定这样的意思。好，大概是这样。那 alpha 跟 beta 是多少呢？下一页。Okay, so alpha, what is alpha and beta? Lagrange multiplier, beta. Okay. So continue this one. This is what we learned from here, right? So this one, we try to solve the beta. So we can compare. We found that, we still have two constraints, right? We need to use that equation. So this is the second equation. We compare. How can we compare? Because we found that here, epsilon j. So we times nj, and then we summation to make the left hand side and right hand side the same. Okay, so we do this one and that one. Okay, and then we go make the right hand side and this one. Okay, so natural log W, yeah, we know that in the previous page, right? Everything in the gray rectangular means that you have known that, I have taught that. Okay, so we just directly compare what we learn. Don't you think these two guys are the same? Okay, so they are very similar. So we can substitute this, become natural log W, natural log W equal to natural log n factorial plus n minus alpha n minus beta u. So all these are constant. Okay, so natural log W equal to C is a constant, minus BU, so this is a constant. Okay. Right. So natural log W equal to C minus beta U. And then if we can bridge in by statistical thermodynamics to classical thermodynamics, so the S equal to K natural log W, so we just times K here, Kc minus Kbu equal to blah, blah, blah. The Kc, of course, is another constant. Okay, so K beta U minus, so S equal to S naught minus K beta U. So if you do the differentiation to the internal energy, it just left minus K beta. Okay, so this one is okay. We come from here. For the classical thermodynamics, you just do this ds. You can have another form. I believe you are quite familiar with that. And then we can compare. Oh, they are the same, right? So we directly, these two things, right? So we can have beta equal to -1 kT. Okay, so that's how we obtain beta by using classical thermodynamics, what we learned in the previous few years or few weeks ago. OK， 好，那我们刚刚算完那个 GJ 跟NJ 的 ratio 要等于某个某个数字。好，那接下来我们就要看这个到底那个 beta 到底是多少。那 beta 到底多少，我们就开始要去运用刚刚的 constraint 嘛。好，我们有2个 constraint， 我们要把它用掉，那才能解得完嘛，对不对？好，那我们就用掉它。那我们看一下这个式子。好，前面那个式子发现，epsilon j 跟有点像哦，这个 u 有点像，尽量让左边的式子跟右边的式子连接起来，所以我们就全部同乘 nj， 然后把它 summation 起来，得到这个式子。那得到这个式子，我们就会发现，这个东西跟我们之前 natural log w 的某2项很像啊，所以我们就把它这个 natural log w 带进去，然后就可以得到这样子的式子。所以我们的 natural log w 就变成一个常数减 beta u 啊，这个 c 就是常数减 beta u。那如果 natural log w 乘上一个 k 的话，不就是就是那个什么s 吗？哈 s， 所以是 s 等于 k natural log w 就变成长这样子。那如果我们今天对internal energy 内能做微分的话，就得到这个式子。好，那接下来呢，我们又看到 classical thermodynamics。classical thermodynamics 的话，我们这边都会了嘛，哈，就是这边你以前都有写过。那这个写过的话，你应该说这2个式你都分别写过。好，那我们就可以比较这个系数。du 的系数的话，那不就是跟这个一样吗？那我们就可以得到 beta 等于-1除以 kt。好，6分钟。那接下来呢，我们就可以继续算 alpha 了。So now we continue for Lagrange multiplier alpha. So alpha is similar. If you are going to use n, right? Previously we used u, now we use n. So nj over gj equal to exponential alpha plus beta epsilon j. This is what we learned, okay? And we want to compare. This means this red arrow means compare, right? So compare the left-hand side and right-hand side. We found that all we need is just summation, okay? With summation nj, and then we will try to make the right-hand side and left-hand side the same. So n equal to exponential alpha is go out to the outside of the summation because they are constant. Okay, so it looks like this, ugly, but it's okay. Exponential alpha equal to these things to the left. Exponential alpha equal to this one. So we obtain that. Ta-da. Boltzmann distribution function, the probability of occupation of a single state belonging to the jth energy level looks like this. Fj is Nj Gj ratio equal to exponential alpha plus beta epsilon j, and now we know alpha beta looks like. So it's actually n exponential minus epsilon j, kt, summation n j equal to 1, gj exponential minus epsilon j kt. Okay, so that's it. Whenever the nj and gj ratio equal to this, it will make the possibility the highest. Okay, and then we will name it the ugly term in the bottom is partition function z, and z is sum over state, just like we mentioned before. Okay, and notice that there's one thing you can notice, that epsilon j is actually proportional to 3 volume, right? Volume. So which means that the nj is related to, I mean, you can see this function. Mj is controlled, determined by epsilon j and temperature, right? Because apart from these two things, they are all constant. So epsilon j and t will determine nj, right? So nj are determined by temperature, of course, temperature. What is v? V control epsilon j. So n are controlled by temperature and v. In our classical thermodynamics, T and V also define a state. So you can see they are matched. They have the same conclusion, right? Very good. That's it. So that's what we are going to say. 好 ，alpha。应该说第一个 Lagrange multiplier， 刚刚是算第二个 beta 吧，现在算第一个。那第一个很简单，我们把第二个的 constraint 用掉了 ，u 的那个用掉，现在变成 particle 的总个数要用掉，所以呢，我们直接把它 summation 起来，就可以把左边跟右边比较啦，哈。那比较完以后，我们就发现，exponential alpha 会等于这个东西。OK， 那我们就把它写下来了。exponential alpha 会写成这样子了。所以呢，还是一句。就是很重要的，就是我们要怎么样找到 N1、N2、N3 它的长相呢？我们只要去看这个 N1、N2 啊，它的在那个阶里面，跟它自己那一阶的 degeneracy 的个数的比值要等于这个人的话，那它就会是最大的几率。OK， 那这个值要怎么去决定呢？就是 epsilon j 跟 t 来决定的。epsilon j 我们之前用 particle in the box 对不对？算过，它跟体积 有关，所以你只要体积跟 temperature 决定了以后，你就决定了 epsilon J T， 所以你可以决定了 NJ， 也就决定了你最稳定的状态是什么状态了。OK， 所以跟我们的那个什么 classical 是一模一样的事情啊，就得到一样的结论，非常棒。OK，that's it. We will have 20 minutes break, and if you have any questions, just let me know. Thank you. I will see you later.
第二件事只是画错了，
我错了，有吗？
因为这样好像是 N1 的 G1 次方，这应该是有
我的意思是指说，等一下，G1 degeneracy in energy level 1。没有，他的意思是指说，它有这么多格可以让你放，你可以第一格放 N1 格，第二个也可以放 N2 格，第三个讲错了，第一格可以放 N1 格，第二个也可以放 N1 格，它有这么多种选择，所以应该是，我看一下哦。Yeah, in energy level 1, how many possibility? G1 N 值没有错，但是我画错的意思是这样吗？
应该是。
我来想看，你也这样觉得吗？
那这边我也是搞不太懂。
值没有错，但是我画图画错。那我想想看，我那时候是怎么解释的？G1 N1 there are G1 degeneracy in energy 1 how many possibility 我有 N1 颗，然后我 G1 个 degeneracy 对 G1 的格子，所以 G1 的格子是没错的呀。你可以把 N1 全部放在1里面，你可以把 N2 全部放在N1 全部放在2里面。但如果你这个的画法，就会是你这一颗有 G1 个选择，对不对？然后
是不是例子去选 degeneracy？
对，让我思考一下哦。对啊，为什么那时候是这样画？There are G1 degeneracy。好，你让我想一下，我自己坐在这边想，我比较那个比较稳定一点。谢谢，我想一下哦。 这样画比较对吧？嗯，好。哎，刚刚那位同学，好，没关系，这样画就对了嘛。好，那我改画法。好，等一下就这样。那请大家再两位告诉我你们的学号，这样。好，还是你现在可以给我，谢谢。嘿，请问，
就是
这样画就对了嘛？哈，好，那两位可以把那个学号写在这里，谢谢。这样比较好理解哈。OK， 好，谢谢。我在课堂上有讲错吗？还是说我只是画图画的不是很好而已？
好像是就是画图看不懂。
画图看不懂。
对，
好，
因为那时候的方法好像感觉是这 N 万颗都要放同一个。
对，
哦，不是，是，好，没有关系，反正这样画会比较看得懂，对不对？
对，
一颗有 G 个选择，这种感觉。
好，谢谢老师。
好，你还有什么问题？
就是我觉得，就是我们要怎么样理解那个 multiplier？就像之前 那好像这好像是力学里面都会出现，
对，它就是一个最佳化的，它是一个最佳化
微
的过程。
分方程做了一个技巧。
对，它是一个技巧。
之前好像量子力学很常出现那个Hamiltonian，就是这种数学运算子，然后我就想说，我们这种就是不是物理系出身，就要理解这些东西。
它其实是数学啊，它其实是一个最佳化的方法。因为它要满足所有的条件。然后要满足所有条件，表示说，一方面它要最大化，二方面又要满足条件，因为正好满足条件那个就是这个等号会等于一个数字嘛，就是那个 constraint 啊，它会等于一个数字，因为它既然是数字的话，它微分就会等于0，所以它正好跟你的最大化微分等于0是相同的算法。所以他就把它整个加在，就是定义成新的函式，然后这个函式只要每一个参数微分等于0的话，它就刚好符合所有的事情。它就是，
所以它是我们很难不加这些 multiplier 去解这个东西。
让我思考一下哦，如果不加这个要怎么解啊？
这好像是那个一些物理学家千锤百炼的结果。
让我思考一下，要怎么样？如果不用 Lagrange multiplier 要怎么解这个式子？但实际上你也不用去，就是它应该这样讲，它这一个，让我思考一下哦。如果不用 Lagrange multiplier 要怎么解？其实 Lagrange multiplier 就是微分啊，就是微分等于0，其实跟对啊，其实就是微分诶。它其实取个 fancy 的名字而已。对啊，不觉得吗？它就是微分。然后其实跟牛顿法其实也好像也没什么差，它就是微分找到极致。然后应该这样讲，简单的最佳化就可以用这个方法，但是不简单的就不能用这个，
因为它只有一个峰值。
对，它只有一个峰值，但其他的如果多个峰值的话，这个早就完蛋，所以才变成牛顿法，就是猜一个点，然后开始去找斜率。所以其实这两件事情其实是一样的，只是这个是可以直接算出，就是因为它单纯，所以就直接可以算出来一个，它可以直接用笔就可以算出来。但如果是一般的这种，你看过常常那种最佳化用牛顿法找的，那就是比这更复杂。我相信是这样，所以它俩其实是一样的事情。我觉得是这样。谢谢。 最近买了一个机械式键盘，好像是是个红轴吧，我忘记了，对不起。反正学员推荐我就说要有感觉，但是又不要太吵的。然后他就是青轴还是红轴啊？红轴吧。然后我就买了，然后我就我买了2个，一个放在办公室，一个放在我家。好，不要检举我。好，我在家工作的，对不起，我真的是在家工作，我每天工作到一两点。哈，如果我的学员都知道，我1、2点还会传东西给他，所以我在家工作，就原本我是使用笔电，然后打的就很不舒服，然后我就带了，我就买了那个键盘，然后就回家打了这样。然后真的就是感觉起来就是晚上就很想要打字，很想要打报告，然后就想要打。好，那结果呢？以前呢，我就是用我的餐桌当做是我的办公桌，然后我就是因为笔电嘛，就这样拿出来，然后就坐在餐桌开始打字，然后打，然后工作到1点多、2点多，好，我就睡觉，这样。然后啊，现在拿了那个键盘很大一个啊。所以我等于是笔电在键盘，再加滑鼠，所以就是要收的东西开始变多了。然后我就觉得不能用餐桌了。你知道，你有听过一个故事吗？就是然后故事的主人买了一个花瓶在家里，然后觉得这花瓶好漂亮，然后开始换桌子，然后换桌子完觉得然后就开始换窗帘，然后到最后整个就是我就开始去弄。我说不对，我不能坐在餐桌上。然后我就必须要去找新开发，在我家开发一个新的地方，然后可以摆桌子，这样子我就可以，你就会发现，其实我是一个我在家里是没有桌子的人。我的小孩有桌子，我太太有化妆桌，但是我自己没有桌子。然后我后来好不容易找到一个可能放下我的桌子的地方，阳台。所以我就坐在我的阳台工作了。现在开始从今天开始，我就是坐在我阳台工作了。对，而且我的桌子是什么，你知道吗？是那种可以收纳的露营桌。也就是说，以后要去露营的话，我要把我的桌子拿出来，然后把它卷起来，然后带去露营。然后我就忽然想说，奇怪了，就是我在对我家的贡献，说实在，我觉得我对我自己觉得是我对我家的贡献，劳力、金钱什么东西都是应该是 top 的，但是我的地位就是最低的，就连我都自己没有我自己的房间，然后我的桌子也没有，然后我竟然要用露营桌来当我的工作的桌子，然后我的房间竟然是阳台，然后昨天晚上就忽然有个心酸感，然后这时候就想。对啊，你看日本的那些爸爸，对不对？都是地位最低的，连狗都不如的那种。对，我想说，果然好像就是这样子。你为一个家庭做牛做马，那地位就是做牛做马。对，这都是我的体认。对，这就是，唉，对，就这样，这是我的体认。大家觉得怎么样呢？好，哇，英文啊，太震撼了嘛。然后英文就是。I just bought a mechanical keyboard and I found that it's really enjoyable when I do the typing. And I took them to my home and I found that I need a proper desk to place the mechanical keyboard. And then I found that I don't have enough space for myself for proper desktop in my home because all the space in my home occupied by my kids and my wife. So the only space left in my house is balcony. So now I'm walking at the midnight in the balcony in my house. So I feel really sad because I found that my level in my family members are the lowest. Just like yeah, that's my complaining. Sorry. Right. So last students asked me about the figures. Okay. he said my figure doesn't represent too much, doesn't represent well of this conclusion G1 with the G1 to N1. Okay, so previously I just write down N1, 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 N1. So actually, they think this is kind of misleading. I agree with that. Okay, so I rephrase, replot the figures. Sorry. So which means that there are GJ degeneracy, which means that there are space that available. Okay, available. GJ space available for the particle, and there are N1 particles waiting to choose. Okay, so which means that the number 1 particle has G1 choices, and N2 particle has G1 choices. Okay, so G1 choices for N1 particles. So G1 to N1. Okay, so I believe these figures are better than what I plot in the previous few years. Okay, I agree with that. Okay, so I changed to this, which can help you more to understand this. Right, that's it. Or if you want to do this. Oh, another thing is that thanks to the video uploading, and I can save 2 weeks. Originally 2 weeks we cannot have any lectures, any physical lecture. But now I upload video, so which means that I can save 2 weeks or more. So which means that I guess we can have our midterm and final set. Midterm should be next week. Okay, next week for 4, 5, 6 PDF. Okay, and so I suppose this week or next week I can finish the chapter PDF 6. So next week I will teach PDF 7. Okay, so I believe we can. Everything will be on the progress, and I believe you can do the buy the ticket. Buy the ticket if you have the plan right after the semester, the end of semester. Okay, so yeah, I will say. Sorry, I need to see the actual date. 29th. Right, 29th is the, how to say that, the pre-sports event. Does anyone attend this pre-sports event? 预赛，他说全校运动会预赛，有人需要去那里吗？如果没有的话，我就要期中考咯。OK 哈，应该期中考不是那个预赛应该是大学生吧？我们现在研究生应该不玩这个吧？应该会被大学生电吧？大学生太年轻了。好啦，那29号哦，期中考 PDF 4, 5, 6, 7. 29th of November, midterm 2. All right. 29th of November, midterm 2. And I hope, not set yet. Okay, don't write it down. I hope I can make it 27th as a final exam. 27th of December. Okay, I just said, not plan. Don't just memorize it. Okay, don't write it down. I just plan. But 29th of November should be midterm 2. Okay, so please tell your friends and classmates. Okay, 不用讲中文吧？好，谢谢大家。Okay, let's go. 对啊，昨天晚上就是工作到1点多，然后坐在阳台，我就觉得 有点冷。当然了，我的阳台是有那个啦窗户的啦，是室内，算是室内哦，算是室内。但是就是听外面的风很大，我觉得我在那边打字，坐在阳台。哎，好了，就这样。这就是爸爸，OK. Right, so let's talk about let's practice examples. Consider a system of n distinguishable particle. So it's go for Boltzmann statics, right? At temperature T, while available energy level epsilon 1 and epsilon 2, and epsilon 2 is greater than epsilon 1, only 2 available energy levels, which means that this is a toy model. In the real world, there will not be only 2 level, right? So energy level 1 and 2 only is a toy model. So the behavior later will be fake. Okay, it's not true. It's just a toy. Okay, just playing around to let us practice. Okay, so don't make this real. And just practice. Determine the equilibrium values of occupation number N1 and N2 and the energy level, energy U of the system. So you set T and U and of the system as a function of temperature. Okay, G1 equal to G2 means that degeneracy of energy level 1 and 2 are the same. So yeah, determine equilibrium values, and B, show that specific heat is given by this one, okay, and where triangle delta equal to epsilon 2 minus epsilon 1, okay, examine the low temperature, and high temperature behavior of CV divided by NK, and sketch plot this, okay, and a function of KT over delta. So what they are doing is actually the chapter 14, 15, 16 we're doing in the future. So they're kind of examining the low temperature behavior and high temperature behavior of materials. Okay, so yeah, this is your first try. So now only two energy level. Ni equal to Ngi exponential minus epsilon j divided by Kt divided by Z. Of course, Z is sum of all states. So which means that in this very first example for you is only G1 exponential epsilon 1 kt, and this is G1 exponential minus epsilon 1 kt plus G2 exponential minus epsilon 2 kt. So this is sum over state, the only 2 energy level availables here, and also G2, G1 equal, so you can divide by them, and this is G1, N1. N2 is, let me just write it down, exponential minus epsilon 2 kt, and epsilon minus epsilon 1 kt plus epsilon minus 2 kt. Okay, so N1, N2 looks like that. And this is occupation number. So AU is summation epsilon j, Ni equal to, tired, N epsilon 1 exponential epsilon 1 kt plus epsilon 2 exponential minus epsilon 2 kt, and exponential minus epsilon 1 kt plus exponential minus epsilon 2 kt. Okay, so this is U. And then if you want to change to the delta, in the second epsilon 1 for second problem, epsilon 1 plus epsilon 2 exponential minus delta kt. So 1 plus exponential minus delta kt. Okay, basically these two things are the same. Okay, but we just change epsilon 1, epsilon 2 minus epsilon 1 as the delta, and so you can make the u as another form. Okay, problem A is okay, easy. B, CV, well, later. Okay, so again, only two energy level. All right. This is toy model. Toy. Okay, so your CV equal to, you see, after we connecting our W or N1, N2, N3 set with internal energy or entropy, and then you can calculate whatever you want in the classical thermodynamics. A CV. CV is the partial U over partial T. That's constant V. So just do the differentiation. NK epsilon 2 minus epsilon 1 KT square exponential minus epsilon 2 minus epsilon 1 divided by KT 1 plus exponential minus 2 epsilon 2 epsilon 1 KT 2. Okay, so delta. This is delta, this is delta, this is delta. Okay, so this one, fit that one. Good. Okay, and then we can sketch. We can sketch it maybe by using Excel, maybe. You just substitute the CV over NK. I mean, just put this to the left hand side. This is Y, okay? And the right hand side using KT over delta. So it's KT over delta, KT over delta, and KT over delta. Okay, so you can become X, X, X. So you have X and Y, and you can use using Excel. Just you can plot this figure. You can see this is low temperature. This is a high temperature. But as we mentioned before, this is toy model. Toy model only have two energy levels. So when you go to the higher temperature, there's no more energy level left to make the particle jump. So it becomes decreased. Otherwise, if you have more and more energy level, it will look like that. Okay? So this is not right. This is okay because energy level 1 and 2 is really for low temperature. So suppose it will be like this. Okay? 好，这个题目是玩具题目啊，它是一个模型题目，让你练习而已啦。哈，所以它只有2个 energy level， 而且2个 energy level 是 epsilon 2大于 epsilon 1，然后 G1 等于 G2。好，那它就要我们算 N1 跟 N2 的长相。它这个长相呢，会让就是那个 W 最高值，那也就是我们所谓的 equilibrium state。好，然后我们就这样算了。那这就是我们的式子嘛。好，但是这个 Z 呢，好像不能带公式，但是实际上它就是 sum over states。我们知道它的意义是什么的话，我们就把 energy level 1跟2就加起来就可以了。它就是分母，然后上面就是它的每一个 N1 跟 N2 的自己的分子，那就可以算出 N1 跟 N2 了。然后有 N1 N2 呢，就可以把它 epsilon 乘上去，就可以得到它的 U 是多少。那 U 是多少？有了 U 了以后呢，大家可以想想看，就是有 U，那我们就可以用 classical thermodynamics 传统热力学的方式去算我们想要算的东西 CV 作为一个微分，就可以得到这个式子。好，所以这证明也是很简单的。那我们用这个东西呢去画 Excel， 就画出这条线。好，那这条线呢，你会发现它的 low temperature 跟 high temperature 的 behavior 的行为是不一样的，是这样子，这样子。那一样，这边怪怪的，为什么？因为这边没有在更高的 energy level 让它爬了，所以它越高温，它就没东西可以爬嘛，它就会聚集在 energy level 2。那但是实际上，真正有 energy level 让它爬的话，它的 CV 应该是要长这个样子。好，就这样，以后会讲14章、15章、16章，就会用这样子的方式去检验一个材料的 CV 的比热。好。Next one, we are going to talk about another distribution. The previous one is Maxwell distribution. Now it's Fermi direct. The Fermi direct distribution is set for the particles are identical and indistinguishable. Okay, indistinguishable. And because we're talking about the fermion is a particle that angry with others. They are not good at dealing with others. So once it occupies a degeneracy, they cannot share with others. Okay, so this is called Pauli exclusion principle. Okay, only one. So fermions like electron and neutron, because it will Pauli exclusion others, so exclude others. So it occupies the space volume. Okay. So useful for study the free electrons in metals or semiconductor. Okay, good. Remember this, metal and semiconductor, because that's how you apply the Fermi direct. So when you see a material in front of you, you can choose which distribution should apply to that material. So when you're dealing with metals, you go for Fermi direct. When you're dealing with semiconductor, you're going to go for Fermi direct. Okay? Now, let's take a look. When you are considering a fermion, trying to find the degeneracy to occupy, so this is one energy level. Jth energy level, just like a bookshelf. Okay, bookshelf. You have many level of bookshelf, and then there are some box. The box called just like the degeneracy. You can put the particles in that box, in those boxes. Okay, and you find that you put it, Nj of the state are occupied, and G, and you can see this is 1, 2, or 3. So Nj boxes are occupied. The rest of it, empty, will be Gj minus Mj. Okay, Gj minus Mj is the state are not occupied. Do you think this is quite familiar with? It sounds familiar with for you because it's kind of coin tossing problem, tossing experiment, right? Because this is, so the W equal to M factorial N1 factorial N minus N1 factorial. Don't you think this is kind of similar to head and tail, right? Head and tail. So you can use this. If you understand this, it's kind of really similar. Really similar to what we're going to do. So this is Wj equal to Gj factorial, Nj factorial, Gj minus Nj factorial. So you can treat that GJ is the total number of coins, and NJ should be the head, and GJ minus NJ should be tail. Okay, so very similar to that. 好，我们现在讲的是 Fermion direct distribution 分布。好，这个分布怎么想呢？就是我们现在面对的材料，好，它的 particle 是 identical 的，是就无法分辨的。然后它是不能，它是相同的，然后它不能被分辨的这样子哈。然后它是 Fermion， 然后 Fermion 的话，它就会占据一个颗粒的能阶，它是不能跟别人分享它的 degeneracy 的，好，它会叫做包粒不相容原理。那它其实就是 Fermion， 其实就是电子啊什么的哈。好，那这个是。只要我们在学习一个材料，它是有 free electrons 的电子的东西呢，我们就适合使用 Fermi direct distribution。所以啊，我们要去看到一个东西的时候，我们要去选择对的 distribution。好，那我们就可以想象一下，这个 level 就像一个书架一样 ，energy level 就是个书架，然后它上面有很多 degeneracy 嘛，对不对哈？所以就好像是书架上还有很多小间隔、小书盒好了哈，书的盒子。那这个盒子它可以让那个 particle 去选。那例如说这边有 NJ 的 particle 放在这里的 energy level， 就是它有 NJ 个颗粒放在这个能阶里面的话，那就其中有 NJ 个被占据了，那剩下的就是 GJ 减 NJ 嘛，哈，就是剩下的是空的，好，那你不觉得跟我们的那个丢铜板是很像的吗？哈，那N 的话就是我们的 GJ， 就是所有铜板的个数，然后 N1 就是头的个数，然后正面的个数，然后 GJ 减 NJ 就是反面的个数，好，所以基本上是一样的，就可以写成这样的式子 WJ。Okay, so next continue. Level J equal to this one, WJ equal to this one. So the total number of microstates to allowable configuration should be times. So here become WFD. You see WFD with the Fermi direct. Okay, so it looks like this. And maximize. Now we need to maximize that. This is our goal, right? We want to maximize the WFD by giving a set N1, N2, N3, Nn. Okay, but now based on our previous experience, WFD should be natural log. Okay, so we do the natural log WFD. We do we do this. Okay, and then we do the Stirling approximation. Become okay, and yeah, and again, we found that this one, the first term, will not affected when you do the partial differentiation for NJ, GJ natural log GI equal to 0. So it won't occur, the first term won't occur in the next few equations. Okay, and also we need to subject to Ni equal to N, Ni epsilon I summation equal to U, and we do exactly the same Lagrange multiplier. This is Lagrange multiplier formulation. Okay, formulation. So this is equation. We do exactly the same thing. Okay. 好，那接下来我们写了 level J 长什么样子了嘛，对不对哈？这里，然后我们就把它全部乘起来，有多了那个拍啊，它就是连乘。连乘以后一样，还是要去找到这一个 N1、N2 长什么样子，会让 WFD 最大值。但是一样，基于我们之前的经验 ，WFD 要最大值很难，我们就做成 natural log WFD 的最大值就好了。反正最大值 natural log WFD 的最大会让它最大值的，也会让 WFD 最大值。好，所以说这两个东西带进去都会让它最大值。好，那我们就开始 natural log FD 会长这个样子，然后做 Stirring approximation， 把阶层都做好。然后做完以后呢，第一项终究还是不会跟 NJ 有关系，所以第一项我们就可以不用管它啦。然后接下来一样是 subject to， 就是两个束缚条件，然后一样做 Lagrange multiplier， 噔噔，然后就去做微分，就可以解出所有的 N1 要长什么 NJ 要长什么样子了哈。然后还有 alpha 跟 beta。好 ，next， basically we do exactly the same thing. So the Fermi direct distribution, we do the differentiation. Again, there's no G terms, right? Nothing here in the previous page. So this is a formulation. And then we do the differentiation. We find that NJ, ta-da. So become here easy. And then continue. NJ equal to GJ equal to 1 exponential minus alpha minus beta epsilon j plus 1. Okay. So you notice that it has one more term, 1 plus 1. Okay. And then if we want to solve the alpha and beta, we compare this u and compare this n. Unfortunately, because of this plus 1, it doesn't work anymore. So, okay, now we set alpha equal to mu over kt and beta minus 1 over kt for now. Okay, for now, we will explain this later. Okay? So we just set that because it doesn't work by solving the u and n, it doesn't work. So we set them, and then we have reason. We will explain that now, later. Okay? So if you accept this, alpha and beta, write it down, and plus 1. Okay, so fj equal to 1 over blah, blah, blah plus 1. It's called Fermi direct distribution. Okay? And then we will explain later. Okay, don't worry about that. 好，那我们就开始把那个刚刚的算出来嘛，哈 ，Lagrange multiplier 就是把它算出来，算出来以后呢，得到一个这个式子，这是+1，不小心分母多了一个+1啊，结果呢，就造成了我们之前去比较系数的方式无法成功了，因为多了一个1就变麻烦了哈。那 doesn't work 啊，怎么办呢？所以呢，阿法贝塔目前算不出来，我们就先把它设定成这个哈。但是我知道大家会一头雾水，但没有关系，我们等一下再解释。那如果你可以接受这个的话，我就先接受 Fermi direct 长这个样子咯。OK。对不起。好，那如果这 OK 的话，我们就继续看下一个 Boson-Einstein distribution。那刚刚是对 Fermi 嘛，现在可以变 Boson。Boson, the Bose-Einstein distribution, the particle is identical and indistinguishable. 一样。But they do not obey the Pauli exclusion principles. They can share. Okay, the same degeneracy, because we'll talk about boson like photons. So they're not occupying the volume. Okay. Now, how can we dealing with that? We imagine there's a bookshelf. Okay, the energy level looks like that, and then we have particle to separate. Okay, and then we have a partition, book partition. Okay, so you can imagine that previously we're using books, right? But now it's easier for us just arranging particles and lines. There are many permutation, arrangement. You can have particle partition, and no particle partition. Okay, so you can do many possibilities like something like that. You have many choices arrangement for these line and particles. How many particle? Nj particle. J's level, right? Nj particle. Identical particle. Nj. Yes. How many degeneracy and partition? Gj minus 1. Okay. You see that? How many degeneracy in this case? For this case, 1, 2, 3, 4, 5, 6, 7, 8, 9. Gj equal to 9. But how many partition you have? 1, 2, 3, 4, 5, 6, 7, 8. So it's kind of, partition, just separate them, but you have one more degeneracy. So if you have degeneracy Gj, you need to minus 1 for getting this partition, right? So now how many ways? How many ways? How many ways? Nj plus Gj minus 1 be arranged into Gj minus 1 lines, or we can say wall, and Nj particles. Okay. The answer is Wj equal to Mj plus Gj minus 1 factorial divided by Mj factorial Gj minus 1 factorial. Okay, so that's how we did this. OK， 好，要讲的是 Bose-Einstein distribution 分布。这个分布是针对 Bose 波色子，它不会占据空间，因为它不会排斥其他人分享 degeneracy。OK， 那这时候就可以，就是因为它的行为不一样，所以我们要不一样的方式，就可以想象看，这是一个能阶，这个能阶上会排列。其实刚刚是说是 box 嘛，对吧？一个 degenerate 好像是一个盒子一样，但是现在不对了，因为现在盒子感觉起来要排列的话，你还要去考虑它里面有几颗，对不对？那这样很麻烦，不如把它改成这样好了，我们改成墙壁好了，我们改成圈圈墙壁，圈墙壁，没有圈墙壁，就是你可以去排列圈圈跟墙壁啦，到底有几种算法，几种排列方式？那反正隔完以后。像这边就是这个 degeneracy 就有2颗，这个 degeneracy 就没有，这种感觉。好，那现在就要看啦，有 Nj 个颗粒没有问题，但是有几个强啊，其实是 Gj 减1哦。原因是因为你看这边有几个 degeneracy 啊，我刚刚算过了，有9个对不对？但是你现在只有8个强，也就是头尾问题啦头尾问题。好，总之呢就是 Gj 减1个 partition， 那这时候我们就要问啦到底有多少种方式把总共 Nj 颗跟 Gj 减1个强排列好，到底有几种方式可以排列呢？就是这么多种。好，大概是这个样子。So we will do exactly the same thing, Bose-Einstein distribution. Our level Wj become Wbe with the multiple times pi. And we maximize natural log W, B, E, right? Bose-Einstein. And then we do exactly the same thing. And then we do the Lagrange multiplier formulation. we do exactly the same thing. No need to say. 好啦，基本上就是做一模一样的事情，只是现在变成 natural WBE 啊，只是换了一个字而已。那现在就等一下就可以继续做下去了。Okay, so we will have 10 minutes break and we will come back to solve Bose-Einstein distribution. Thank you. 请说。好像是好像是
少 n 的。
对，少 n，对，少 n， 没错。少 n 对，没有错。这个第二个少 n， 对。
提早10分钟下课。
为什么？
是11点才下课。
哦，提早10分钟下课啊！好啦，11点再上课哈，提早10分钟上课。I'm sorry。好，来，请写你们两个的号码在上面，谢谢。哦，提早10分钟下课啊。哦，11点上课。
OK。
那如果11点上课的话，还是要上到12点。对不起，不好意思，昨天熬夜，脑袋有点不太清楚。嗨。
你有提到说第二次考试的范围是4到7还是4到6？4
到6。
因为老师第二次讲的有点不太一样。
哎，我第二次讲不一样吗？
因为你第一次讲4到6，然后你第二次讲4、5、6、7。
4、5、6，对，然后7、8、9这样，哎，4、5、6、7、8、9。
就是 J 跟 I 是一样的。
对，是一样的啦，哎，是一样的。它其实是一个 self-consistent 的东西，只要这边写 I 就可以了，然后另外一个写 J 也没有关系，这样就是它自己对就好了，这样。谢谢。 喂，好的啊，真的是非常抱歉啊，我的脑袋不是很清楚啊，就是我既然要11点才下课，我50分就下课了，搞不清楚了。好，不过就是11点开始，那我们这一就上整整1个小时了哈，抱歉了哈。那真好笑。然后我刚刚也说，然后有同学跟我说，我的考试范围好像讲2次讲不一样，反正就是4、5、6 PDF 是期中考第2次，然后7、8、9是期中考最后不是期末考，所以就是3张好，接下来就是3个投影片这样子 ，OK， 好，然后刚刚的 N 少写了，这里，这里少写了，好，感谢这2位同学提醒我哦。好，不过我真的觉得你们这一届很棒就是你们找到我非常多的错误，然后而且甚至也会让我的教材更好，那我觉得非常感谢大家，好，这一届真的很棒。那这样感觉起来就是之前你们的学长姐就是看过，可能觉得没有很好，但是也没关系就算了这种感觉。那你们都会回馈给我，我觉得这是 feedback 给我，觉得这是非常好的一件事情。谢谢大家，好，谢谢。好，那就这样 ，continue。Okay, so we just focus. Sorry again. The midterm 2 range should be PDF 4, 5, 6. Okay, 3 PDF files. Final should be 7, 8, 9 PDF. Okay, that's it. Let's continue. The Bose-Einstein distribution after we done the Lagrange multiplier formulation. Okay, and we do the differentiation and again delete it, and we came to here, and then we notice that there's one more -1 here, and it will cause some problem, but it's okay because MJ and GJ, you think MJ and GJ, they are number of particles, and GJ is the number of choices in each energy level. Issue always much greater than 1. So you can neglect the -1. Okay, so the answer will be MJ divided by GJ equal to 1. Exponential minus alpha minus beta epsilon j minus 1. Again, you notice that there are okay, this one -1. So Fermi direct +1. Bose-Einstein -1. Okay, and again, alpha and beta cannot be solved by comparing the constraint 1 and constraint 2. So similarly, we set alpha equal to this, beta equal to that. We will explain that later. Okay, and then the Bose-Einstein distribution looks like this. The only differences will be -1. Fermi direct +1. Maxwell, no. Okay, so that's it. 好，一样做一模一样的事情了哈。那把它做 natural log，就是Lagrange multiplier 了以后呢，然后做微分，然后消掉，会变成这个式子。那这个式子这边有一个-1，然后可能一开始就觉得很恐怖，但是实际上仔细想想 ，NJ 跟 GJ 它是颗粒数跟选择数，哇，这个数量跟1比起来，简直就是天文数字跟1啊哈，所以就是消掉，也不是消掉，忽略不计，然后就可以写成这样的式子。然后这边有个减1，就是 Bose-Einstein 是减1 ，Fermi direct 是+1，然后 Maxwell 是没有这个东西，所以呢，这就是它的 distribution 啦。好，下一个。Next, I'm going to introduce Maxwell-Boltzmann distribution. Maxwell-Boltzmann distribution is actually for dilute gases. I don't know why there's a point here. So this is four. The distribution is 4 dilute gases. Okay, dilute gases. What is dilute gases? Feature. The feature of dilute gases is the particle numbers are much less than their choices because they are dilute, right? Dilute is really rare particles. So the particles are rare. So the particle number is much less than GJ for all the energy level J. Okay? So this is the feature that we are going to introduce in this distribution. So do we need to do exactly the same procedure like Fermi Dirac and Bose-Einstein? No, we don't need that, because if we apply NJ much less than GJ feature to Fermi Dirac and Bose-Einstein, we will get exactly the same thing. Okay, so really interesting. So let's take a look. So firstly, if we apply NJ much less than GJ to Fermi Dirac, it will look like WFD looks like this, right? And then if we apply NJ much less than GJ, the place they affect is this part, right? The this part will be affected because GJ is much greater than NJ, and then it will become this one. Okay, how? By using this. Okay, so let's take a look. This part, here, and then we list them. GJ minus 1, GJ minus 2, blah blah, and GJ minus NJ factorial. So it should be looks like this, right? Okay. And then here is also GJ minus NJ factorial. So let me take a look. Right. Wait a minute. GJ minus NJ. GJ minus GJ minus okay. Yes. Right. So GJ minus factorial can be separated to GJ to the GJ minus NJ plus 1, and then the rest of it. Okay? Right. So now let's take a look. GJ is much greater than NJ, right? So GJ is much greater than NJ. Of course, much greater than 1, 2, and NJ plus 1. Of course, they are all very small for them. And here, GJ minus NJ factorial is finished. I mean, cancelled by the number under the division. So you can see that this is GJ, so become GJ NJ. Okay, so that's the reason why we substitute here, and then we can say approximately pi GJ NJ over NJ factorial. Okay, so it is, if we apply NJ much greater than GJ, the Fermi Dirac will become this one. Okay. Similarly, Bose-Einstein looks like this. I believe you know that previously. And if we apply NJ much greater than GJ to this, what will it be? The place, the part they affect is here. Okay, so we put here to here, right? And then we list it down. Okay, gj plus nj minus 1, gj plus nj minus 2, blah, 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 blah. And you can list it like this. And you notice that, okay, sorry. You notice that the gj, nj is very big, right? So minus 1 is, sorry, nj minus 1 are all deleted because nj minus 1 is much less than gj. Of course, minus 2. And mj minus mj itself deleted. So you can see that gj, gj, gj. So gj nj times gj minus 1 factorial. Okay, so that's how this replace that, and so again we get exactly the same formulation for WBE and WFD when we apply dilute gas condition. Okay, so for the dilute gas condition, we call it Maxwell-Boltzmann distribution, and they can come from Fermi Dirac and Bose-Einstein. Okay, so yeah, that's it. And then we can conclude that WMB, MB Maxwell-Boltzmann, okay, equal to this. So equal to that. Okay, later I will do exactly the same thing to do the natural log maximization, right? But before that, I will try to talk about the exact value and the approximate value, okay? You can see that if you have Fermi Dirac, it's actually greater than the exact value because you are eliminating the minus part, right? In Fermi Dirac, you should minus that, but you neglect that. So actually, this value is actually greater than expected, the exact value, because we neglect. Because we neglect the minus term. So the actual value will greater than exact value. So sorry, the approximate value will greater than exact value. In contrast, for Bose-Einstein, you see it neglect plus thing, right? So in neglect plus. So the value is less than exact value. So later you will see these three functions in the plot. They will converge to Maxwell-Boltzmann distribution, but the one is above it, the other is lower than it. Okay, so they are converged with two different bounds. Okay, so yeah, let's just give you some more information about this. Then let's maximize the WMB. Do we need to do that? Actually, hey, we can use some interesting. We can become lazy. We don't need to do that again. We can use our smart and makes ourselves lazy. Okay, let's compare a little bit. Let's compare a bit. So now, you have WB. That's you learn in the first page, very first page, right? So the WB looks like this. And if you do the natural log WB, it looks like natural log m factorial and plus a. This one is exactly the same as WMB. Okay, so the WB is actually the m factorial WMB. Did you see that? Actually, if you want to maximize WMB, or you want to maximize W natural log WMB, it's actually exactly the same thing to maximize natural log WB. Okay, so this term differentiation and differentiation. Natural log n factorial equal to 0. So actually, the set of W1, 2, 3, N1, N2, N3 will maximize WMB. It is the same set to maximize WB. So actually, they are exactly the same. So you don't need to calculate that again. Just copy the Boltzmann distribution. N exponential minus epsilon j over kt. So simple as that. Gj, minus gj, epsilon j kt. Okay, that's it. It's Maxwell-Boltzmann distribution, which is exactly the same as Maxwell distribution. Although their statistics are different. Looks like that. But because the only difference is n factorial. But after the differentiation, n factorial doesn't affect anything. So we don't need to calculate it again. 偷懒的英文叫什么？偷懒。可以教我吗？偷懒。我刚好想讲偷懒这个字，但是我不知道英文怎么讲。怎么讲？偷懒。拜托教我一下，有没有人会啊？举手。偷懒。拜托来。我 get a shortcut， 哎，不错哦。get a shortcut， 你可以 get a shortcut， 好哎。可是它没有懒这个东西，它字变成比较快。我想要就是说我想要很安逸的、舒服的，就是我可以做少一点工作，但是我可以得到一样的效果。啊 ？Slack off， 我怎么没听过这个字？好强哦 ！Slack 不是拖延的意思吗 ？Off 就是偷懒的意思。可是这个偷懒有比较有效率吗？好像没有 ，slack off 好像就是糟糕的事情。但是我所谓的偷懒是指我不用花那么多心血，但是却又可以很做得很好这样。slack off 我觉得蛮 negative 的，对不对？但是我这个偷懒是，我觉得 get shortcut 是很好的 ，get a shortcut 好像 get shortcut 比较好，哎。但是你这是比较你真的是偷懒，这懒是不好的偷懒。他这个 get short 好像比较好。好，谢谢大家。那好，谢谢两位，不然两个都加分好了。get short card， 好，你的号码是？等一下哦，41啊，4126130030， OK， 那你3126130117，好，所以我们来说个叫做我怎么写啊？叫做 get a shortcut， 这样可以吗？耶，这样，耶。OK， 好，就这样。好，讲中文了。哎，我刚刚有讲中文吗？还没有吧？还没。好，我们要做 Maxwell-Boltzmann distribution 分布。这个分布是给 dilute gas 就是稀疏气体，其实就是 ideal gas 啦。哈。那稀疏气体有什么特征呢？就是它很稀疏，所以它的每一阶的颗粒数都非常的少，所以它的选择就超级多，选择超级多 ，GJ 超级多，所以远大于 NJ 的意思。好，那我们要去重算它，不用。其实我们用 Thermodynamics 跟 Bose-Einstein 把这个 feature 把这个特征带入进去的话，就可以得到相同的效果。啊，你可以看到这跟 NJ、GJ 有关系的就是这个 term。那 Bose-Einstein 的话 ，NJ、GJ 有关系的就是这个 term。好，那我们这边来把这边仔细的列出来看看，因为下面这边有阶啦哈，所以等一下我只要弄到这个 GJ。阶层只要弄到一半，我这边就可以消掉了哈，所以我就只要弄到 GJ 减1，到之前一颗，然后后面就可以直接消掉。那我们这边发现 GJ 减1、减2、减3呐哈，这些东西都太小了，因为 GJ 超大，对哈，所以我们就省略到后来就变成 GJ、NJ 了。带入进去以后得到这个答案。好，那我们这边答案这个 WFD 其实是比真的还要大的，原因是因为我们忽略的是减掉的东西，好，所以说其实 FD 是比 Maxwell-Boltzmann 还要大的，哦，是这样的意思。好，那接下来 Bose-Einstein 也一样，那我们就看到这个式子在这里的阶层的部分。好，这阶层的部分，因为等一下要跟 GJ 减1 factorial 要消掉哈，所以这边就只要到这一段就好了。那前面那段把它列出来以后呢，我们就会发现 GJ 加 NJ 减1 ，GJ 加 NJ 减2。但是这个 NJ 减1又远小于 GJ， 所以我就忽略，然后忽略完以后呢，得到这个式子，然后这边就会消掉，然后会得到一样的感觉。所以 Bose-Einstein Thermodynamics 运用这个什么，这个 NJ 远小于 GJ 这个条件的话呢，它会是一样的值，而且它因为 Bose-Einstein 是省略加的部分，所以实际上我们的 Maxwell-Boltzmann distribution 它会是小于这个值的，好，因为我们省略的是加的符号。好，然后呢，我们就可以得到 WMB 就长这个样子了，确定了。那我们要去最大化它吗 ？Lagrange multiplier 吗？不用，我们可以 get a shortcut， 我们可以偷懒。原因是因为我们去观察一下 WB 跟 WMB， 我们之前算过的东西，只差一个 n 阶，对不对？你看，只差一个 n 阶。那只差一个 n 阶呢？如果今天我们要去做 natural WB 的最大化的话，我们就 natural WB 会分成两个式子啊，结果两个式子 n 阶啊，我们要 differentiation 它的话，它是一个常数嘛，它绝对等于0啊哈，所以说呢，你的 WB 跟 WMB 会让它们最大化的 N1、N2、N3 其实是长一模一样的，好，所以我们就直接照抄就好了，就这样，答案就这样 ，OK。So let's have a summary. Summary. The statistic and distribution. So the statistics is that you examine the behavior of the particles and the materials, a system, and then you write down how to describe that. The statistics is something you're describing something. But the distribution means that you want to maximize this. The NJ, N1, N2, N3 looks like the distribution of N1, N2, N3 will maximize the W, the statistics. Okay, so these two things are different. This is solution. This is how you describe this system. Okay, so don't forget this. Don't mixing up the statistics and distribution. And Boltzmann is something that really, the important is that they have the n factorial. Okay, and Thermodynamics has +1 and -1. All right, and you see there's nothing here. So this is a summary, and please take a look. 好，这边比较重要的是就是一个怎么讲汇整，然后汇整有一个统计跟分布。统计什么意思呢？就是 你把描述这个系统的特征的方式写出来，写完以后你要去最大化它。那个 distribution 什么意思呢？是分布的意思，也就是你的这个这是它的解哈，最大化它的解是什么样子？也就是说你的 N1、N2、N3 要符合这个 distribution 才会让 W 最大值。OK， 好，那这边值得注意就是 N factorial 跟跟没有这个东西，是 Boltzmann 跟我刚刚一直都讲 Maxwell，sorry， 应该是 Boltzmann 跟 Maxwell-Boltzmann 的差别所在。然后呢，这边是加1减1哈 ，Thermodynamics 跟 Bose-Einstein。OK， 好，那接下来next remarks just give you another summary. Both statistic is called for distinguishable. Okay, distinguishable. So apply for solids and liquids. Solid because they have crystal system, so you can identify. Distinguish particles by their neighbor. Okay, so the Boltzmann status for solids. Fermi direct is applied to study free electrons in metal or semiconductors. Bose-Einstein applied to gas, depending on the or laser or something. And Maxwell-Boltzmann is for dilute gas, or we can say simpler, ideal gas. Okay? So when you talk about ideal gas, you apply Maxwell-Boltzmann distribution. Okay, that's it. 那再跟大家就是总结一下，就是波兹曼统计是给 solid 是固体的原因，是因为它可以分辨，因为 solid 是有邻居的，可以看它的晶体结构就可以分辨它。那 Fermi direct 的话就是讲就是有自由电子的金属等等的东西，半导体等等的东西。那 Boltzmann 就是不占体积的 gas， 然后 Maxwell-Boltzmann 也不是不占体积的 gas 就是不占体积的东西，例如说 photon， 例如说雷射之类的东西。那 Maxwell-Boltzmann distribution 就是dilute gas， 那实际上就是 ideal gas 的意思了哈。以后看到 ideal gas 就 apply Maxwell-Boltzmann 就好了。接下来要讲的是 connection between classical Next, we are going to consider the connection between classical and statistical thermodynamics. 我的喉咙好痛，我要喝一下水。Get a shortcut.越来越觉得 get shortcut 不错，蛮适合这个的。好 ，OK, the connection between classical and statistical thermodynamics. Thermodynamics expression of internal energy using mj times epsilon j and summing them together become internal energy. So we do the differentiation du and blah 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 and blah blah. Okay. So the epsilon j, where epsilon j is a function of x, okay? Well, I actually don't know why textbook want to write this very implicitly, okay? You write it down in really vague way, very blurry. You write down x, the x extensive property, for example, volume, but actually it's referred to volume. So I don't know why just saying it's related to volume. I don't know why, but we know that epsilon j equal to nj square hn h2 v minus 2 over 3. Okay, we know that. So actually we know epsilon j is a function of v, so the x is actually v. I don't know why the textbook wants to write it down really, subtle. 就是 很隐晦的讲这件事情，我不知道他为什么要这样子做，不过我就照他这样做咯。Okay, but the x is v. So d epsilon j is equal to d epsilon j divided by dx dv, okay, times dv. So this one can be written as this one, right? And then another subtle thing is that the textbook, right, name it as y minus y. Okay, so you just write it down. Okay, du equal to this one, and the second term become minus y dx. Okay, and of course this, if you do the du with constant x, the coefficient will be epsilon j dnj. Okay, right. So analog to classical equation, we can write it down like this: du equal to t ds minus t dv, and we can compare then d bar qr minus d bar wr. Okay, so from this equation we know that dux is actually TdS. Okay, so comparing then this one and that one, we can conclude that if you heat it, it will change the arrangement of particle occupying energy level J. If you do the work, you will increase the energy level itself. That's it. That's the connection. Okay. 好，这边要讲的是课本社会这边忽然提到，就是说他们想要把传统跟统计热力学连接在一起。好，那连接在一起的话，我们就用 U 来连接看看。内能。内能的话长这样子，然后我们就把它分，就是我们如果要改变内能的话，就可以有两个贡献。如果是以统计热力学来看的话，你可以改变 NJ， 然后或是改变它的能阶，有两种贡献这样子。好啦，那这时候课本就很神奇了，就是他用写的很隐晦的方式，很隐晦的方式就写epsilon j 会是一个某个东西的函数。某个东西其实就是体积啦，因为我们就知道，我们之前都算过啦 epsilon j 是跟体积就是相关联的。那所以呢，他就把它写出来，就变成，而且还又提个名字，就是负 y， 就把它写成 y。我不懂他为什么要写这么的隐晦，不如就直接写 v 就好了，很奇怪。Anyway， 写完这个东西以后呢，我们就知道 OK dux 它会是，应该说在体积定的状况下 ，du 的话，它会是这个东西，它会是改变 nj 这样子的，而不是改变 epsilon j。好啦，那我们再继续写，我们用 classical 的方式来写 du 的变化量 ，TdS 减 PdP 没有问题。然后前面是跟 QR 有关，这后面是跟功有关。好，那这边我们就看到dux 其实是 TdS。好，那我们就这样比较一下这两个 term 来比较。我们比较发现，原来我们加热的话会改变的是 particle 的，会激发它上去，而不是改变能阶。但是我们给它功，改变它的体积的话，它就会把能阶自己本身而改变，它不会改变它的颗粒的爬升的数量。Okay, so let's extend. We just illustrate the concept in the previous page. Okay. So basically, okay, 应该没问题。好 ，Okay. So next, if we increase the dqr, it will. This is the figure is nj is the occupation number for each energy level j. This is energy level 1, 2, 3, 4, 5. Okay, and then if you increase the heat, input heat, the previous one, the initial one will become the final one like this. It will excite these particles to the higher energy level. Okay, so epsilon J unchanged, but NJ changed, excited. So it will redistribution of the particles. But if you do the work, no heat flow, so you should be a diabetic, okay? No heat flow, just work. The work will make it initial, final. Okay, if you compress the volume, and the particle won't change, particle distribution won't change, but the energy level itself will change because epsilon energy level is proportional to the volume. Oh, yeah. So here you see volume decrease, epsilon J increase. Epsilon J increase, of course, U increase, of course. Right. So that's the two different stuff. 好啦，这一团片纯粹只是把前面那一页的概念就是画出来而已啦，哈。那我们的分布原本是这样子，那结果加了温就会改变它的 particle 的分布，把低能阶的 particle 激发到高能阶上，还蛮正常的。但如果今天你没有任何的热流，你只是去改变它的体积，给它功的话，它的分布是不会变的，它是整个 shift 往上，就是 energy level 整个 shift 往上，大概是这样子。那体积变小的话 ，energy level 能量个别能量就会增加啊，大概是这样。Okay, let's go back to the chemical potential and alpha. Now we are going to explain why we set alpha as mu over kT. Okay, let's go back to explain what we left over in the previous slides. Okay, so because we're going to introduce alpha, and then we somehow know that it's related to mu, chemical potential. So let's go back to the chemical potential in chapter 9 a bit. So let's review a bit. du equal to TdS minus PdV plus mu dm. Okay, this is you might be really familiar with, but there's a little bit different. I need to mention for you. Note that in chapter 9, we have a mu, right? But now we have another view here, mu dn, right? In the chapter 9, we give a star, okay? The star means chapter 9 view, mu, is 4 kilomole. This is really different. You need to be really careful about that. Mu in here, in this chapter, in statistical thermodynamics, the mu here is actually.
我在 Apple Music 的资料库中找不到此项目，你可以要求播放广播电台，或要求我使用特定 App。
好，谢谢。The mu in this chapter, statistical thermodynamics, is actually the mu star in chapter 9 divided by NA, because the mu here is particle base. Okay, this is a particle base rather than kilomole base. Okay, so this is the difference between the mu. So here, chemical potential on a particle basis. Okay, be careful. So here, the D is not N anymore. It's not kilomole anymore. It's particle numbers. Okay, so this is different. Statistical and classical thermodynamics. The mu has different. It's different. Okay, they are different. So be careful about that. Right. So here, du here we want to see du. So here we want to do the du. F equal to U minus TS. I know that. We know that. So we do the differentiation for dF. So we have df equal to dds minus p dv, blah, 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 blah. You know that. And we found that TDS can be cancelled and the F equal to this one. And then we find mu here equal to partial F partial M T V. Okay, mu equal to this. I guess you know that. You can understand that. So now let's connecting Maxwell-Boltzmann distribution statistic to mu. So now let's wait a bit. So stop by now, and then we approach from the other end. Okay, so we start mu. Okay, start there, and then we come from another Maxwell-Boltzmann statistic. We try to connect them and solve alpha. So using Maxwell-Boltzmann statistics, because ideal guess is always our friend, and we can using this obtain a lot of information. So using Maxwell-Boltzmann statistics, WMB it looks like this, of course, and MJ over GJ equal to this, no problem. And then we're going to connecting statistical and thermodynamics and classical. One, so we have S equal to K natural W, no problem, and we apply the WMB and then we can get this one. And equal to by Stirling, right? Stirling approximation. And this term, equal to N itself, right? And then we found that no, and then we can continue, which is equal to Kn, okay, minus combine these two, become this one. Okay, then looks stuck, right? No, it's okay. We have this one, and we have this one. Yes, and then we can substitute into here, and then we can continue in the next page. Okay， 好，我们现在讲 chemical potential， 化学势能跟阿法这个关系。那当然我会觉得，为什么跟这个关系？因为科学家知道他们好像有关系，所以他们就要两个把它连在一起哈。好，那我们就先从 chemical potential 这边有个问题蛮重要的，学长姐都会忽略掉这件事情。这边的 mu 跟第9章写的 mu， 也就是传统跟统计的热力学的 mu 不一样哦。传统热力学的 mu， 我们这边写一个 star， 这个 star 其实就是第9章的 mu 的感觉哈。第9章的 mu 它是 kilomole base， 它乘底 n， 那个 n 是 kilomole 哦，但是这里的 mu 底 n， 这个 n 是颗粒数哦，所以 mu 会等于 mu star 除以 na， 非常非常重要啊。那就之前就有同学就是没有搞清楚这个状况，然后就会把这两个东西搞混，因为它多出一个 na 啊，小心。好，那 du 等于 TdS 88888，然后呢，我们就把 du 跟 F 扯在一起，然后再做一些微分，就可以得到 mu 会等于这个，我相信大家都知道了哈。好，暂停一下，那等一下我们会等于是我们要把两边接在一起嘛，哈，左边的跑到极限了，我们先从右边来跑，再从右边开始出发。右边呢，我们就使用 Maxwell， 这边就是传统热力学嘛，这边就是统计热力学的部分，开始出发。统计热力学我们使用 Maxwell-Boltzmann distribution， 因为我们就是 ideal guess 会常常都会从这边得到最好的资讯嘛，比较简单。好，我们就用 WMB S 等于 K natural W， 好，算出来以后呢，888算出来得到这个式子。得到这个式子以后呢，不要忘了这边 sigma j nj 其实就是全部的颗粒数，这个还蛮简单的，这常常会用到所以请小心。当你算到这里，这时候赶快很开心，把它改成 n 就好了。好，然后我们就算出来，发现这个东西会变成这样，那这样看起来很恐怖，但实际上我们的 nj gj 正好这个东西啊，赶快把它带进来，就可以是下一页了。Okay, so next, our S looks like this, right? And we substitute this one here, and then we can extend blah, 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 blah. Okay, of course, this Z and epsilon J all come from here. Okay? So if we extend the S equal to blah, 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 that's great. Let's take a look. Again, when you see sigma J and J, this is N. When you see sigma J and J, this is N. When you see NJ epsilon J, sigma J, it's U, right? So S equal to U over T plus NK natural log Z minus natural log N plus 1. Very important S. Okay, S equal to U over T plus NK natural log Z minus natural log N plus 1. So important formulation. Be careful. Okay? And then you find that F equal to U minus TS. So we substitute the S to this S. And then F equal to minus NKT natural log Z minus natural log N plus 1. So you notice that classical thermodynamics property S, F, finally we're using partition function and particle number, we can represent them by statistical thermodynamic things. Wow, done. Yes. And the mu here, of course, we just do the differentiation for F. We just calculated in the previous page, right? So we can have mu equal to blah, 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 and NKT, okay? Sorry, NKT divided by N. So we can cancel each other, and we obtain mu equal to KT natural log N over Z. So you notice that we have S, F, mu in the classical thermodynamics, but we represent them by statistical term Z, N, Z, N, Z, N. Okay? Well connected. So NZ equal to okay. And Z can be obtained by Maxwell-Boltzmann distribution, right? So NZ here, wait a minute. Sorry. Yeah, the NZ here can be obtained by divide by KT and do the exponential. So you can have NZ equal to exponential mu over KT. And we also know that Maxwell-Boltzmann distribution has N over Z term. Lucky, so we substitute here. So NJ over GJ equal to this one. And then, lucky, we have alpha equal to mu over KT. So that's how we get the alpha equal to mu over KT. Okay, and then we found that if mu increase, NZ will increase, of course. NZ increase, actually NV will increase. So actually, not so. We just noticed that Z is proportional to V, and we will explain this in chapter 14. Okay, later we will explain that. 没有电啦。OK。为什么这边会有个绿点？好，没关系。好，讲完了哈，就是我们续上一页，好，把 S 用那个叫什么NJ over GJ 带进去以后，就会得到上面这一长串数字。那很高兴的就是 哇 sigma j nj 会是 n sigma j nj epsilon j 会是 u， 然后我们就可以写成这样的式子。这个式子很重要啊 ，s 啊，那有了 s 以后就可以把 f 算出来啦，然后 f 又可以算出 mu 啊，哇，真棒！我们终于把统计热力学跟传统热力学整个连在一起啦。然后啊，我们就会发现 mu 跟 n over z 的关系，其实我们可以把它反拆解回去，变成 nz 等于这个东西。那 nz 又是我们 Maxwell 的这一项啊，对不对哈？那 Maxwell-Boltzmann 的这一项带进去以后，我就发现 nj over gj 会等于长这个样子。那不就是把阿法解出来了吗？然后呢，我们就会发现，我们再从这边开始看，这边 mu 呢往上变大的话呢 ，nz 也会变大，对吧？那其实这也代表是 n 除以 v 会变大。那这个 v 跟 z 是成正比的，以后我们会讲，好，以后我们会讲。OK， 就这样。好。One important thing I need to emphasize it, very important, very, very important, is that this yellow highlighted equation is based on Maxwell-Boltzmann statistics. So if we have something else, it's not obey Maxwell-Boltzmann distribution. For example, Fermi Dirac. Their S won't be the same. Their F won't be the same. Mu won't be the same. So you need to calculate by yourself if the problem, exam, test has different statistic and ask you S, F, mu, you shouldn't memorize it. You shouldn't just write it down for this. No, you need to calculate by yourself through the same procedure. Okay? Be careful, be careful. 好，这边非常非常重要。虽然这个 S 啊、F 啊、mu 很重要，但是你要注意它是从谁导出来的？它是从这个 Maxwell-Boltzmann statistics 导出来的。所以如果今天课就是考试的时候是说我要讲 Fermi Dirac， 那 Fermi Dirac 它的 S 还是这样吗？不是哦，它会有差哦。F 也会有应该这样讲，不一定会有差，因为它微分的那些关系，但是我也记得不清楚了哈。总之你要自己算算看，有些会一样，有些不会一样。好，所以你要小心这个的式子不要乱硬背，好，不要乱硬背，因为它是 for Maxwell-Boltzmann distribution。如果今天是别的材料的话，那就不一样，你要自己去算哦，好，要小心。Next, an alternative way to get alpha and beta. Okay, this is one way to get it. The other way is still using the WMB Maxwell-Boltzmann distribution. Again, we do the natural log MB because we are going to get natural log W mix to get S. Okay, so yeah, that's it. Let's do it. Natural log WMB. Oh, so you can see that previously we did a shortcut, right? Now we are going to pay back. We still need to do that. So natural log WMB equal to this, and it will approximately equal to I1N mi natural log G I minus M I natural log N I plus N I equal to, by Stirling approximation, right? And sigma I and I natural log G I N I plus 1. Okay, so the shortcut cannot be applied this now. Natural log WMB, we'll try to avoid it, but we still need that. We maximize that, and we find that with the alpha and beta, and we have MIGI equal to exponential alpha plus beta epsilon I. The reason why we're doing this is that we are going to do the natural log W mix. Which natural log W mix? Okay. Which will be natural. Natural. This one. Will equal to minus alpha n minus beta u plus n. Okay. And then we just time k, it should be s, right? So k alpha n minus k beta u plus k n, and you can simply get all the value minus mu over t n plus 1 over t u plus p v t. Okay, when you combine them together, compare the blue arrow. Oh, wow, you cannot see it, right? How can there's actually a really tight, really small light blue. This is a really bad projector, I'm sorry. So actually we compare these three terms, and then we can have PV equal to NKT, and alpha equal to mu KT, and beta equal to minus KT. Okay, so that's it. All right. So this is an alternative way to get this. Yeah, that's it.好，那基本上就是也可以用另外一种方法拿到阿尔法跟贝塔哈，就比较简单一点。那但是就表示说我们刚试图逃掉的 natural WMB 做这个阿尔法贝塔的这个叫什么Lagrange multiplier 这件事情我们逃不掉了。好，没关系，就这样做吧。做出来以后，然后去 maximize 它，然后得到这个东西。好，那我们的 natural log W mix 就会约等于负阿尔法 n 减贝塔 u 加 n。好，那一样，我们乘上 k 以后，就可以把这三个项跟 s 比较，我们就会发现，基本上直接就可以得到我们以前都知道的东西，然后顺便得到阿尔法贝塔。好，大概是这样。时间好像快不够了，需要吗？不要好了，2分钟那就算了。好啦，那今天就上到这里。So I will just finish for today, and we will see you next week. I will finish chapter 6, maybe just 10 minutes or 20 minutes later, okay? And then, so which means that next week we will have midterm 2, PDF 4, 5, 6. All right? Please tell your friends. Thank you very much. Bye bye. 少了右括号，对，少了右括号，对，少了右括号，
就是这个，
对，谢谢你。当然，好，洪亮的话是，
我可以再讲一次，
这个号码，
下面那个，
对，我知道，
好，谢谢，
谢谢，好，请说。
没有，就是同一个挂号。
同一个挂，好，在哪里？对啊，好，你也说一下吧。312613003，OK，谢谢。